Right now, every clock in your city is ticking in perfect synchronization. From the digital display on your phone to the atomic clock that coordinates GPS satellites from the grandfather clock in your hallway to the cesium fountain clock that defines the international second, they all agree on what time it is. This seemingly mundane fact represents one of the most profound mysteries in physics. If Einstein showed us that time is relative and flows differently for different observers, why do all our clocks on Earth march together in such perfect harmony? The question strikes at the heart of one of the deepest puzzles in modern physics. Einstein, as special relativity, tells us that time dilates. It literally slows down for objects moving at high speeds relative to each other. His general relativity reveals that gravity warps time itself, making it flow more slowly in stronger gravitational fields. Given these revolutionary insights, why doesn't the rotation of Earth, its orbital motion around the Sun, and the varying gravitational fields across our planet's surface cause clocks to fall wildly out of sync? Consider what should be happening according to relativity. Earth spins on its axis at roughly 1,040 miles per hour at the equator. It orbits the Sun at about 67,000 miles per hour. Our entire solar system races through the galaxy at approximately 514,000 miles per hour. These are enormous velocities that should create significant time dilation effects. Meanwhile, Earth's gravity varies from place to place. You actually weigh slightly less on a mountaintop than at sea level due to gravitational differences that should also affect the flow of time. Yet, when you check your watch against a clock in another country, accounting for time zones, they agree to within fractions of a second. The atomic clocks used for GPS satellites, internet synchronization, and scientific research maintain agreement across the globe to within nanoseconds. How is such precision possible in a universe where time itself is relative? Dr. Albert Einstein first grappled with this paradox over a century ago when developing his theories of relativity. His work revealed that simultaneity, the concept of events happening at the same time, is not absolute but depends on the observer as frame of reference. Two events that appear simultaneous to one observer might happen at different times for another observer moving relative to the first. This relativity of simultaneity should make it impossible for widely separated clocks to stay synchronized. If simultaneity itself is relative, how can we have a universal now that applies across our entire planet? The answer reveals some of the most subtle and beautiful aspects of Einstein's theories, showing how apparent contradictions resolve into deeper understanding. The key insight is that while time is indeed relative, the relativistic effects on Earth are incredibly small compared to the timescales of human experience. Time dilation from Earth's rotation amounts to only about 200 nanoseconds per day at the equator compared to the poles. Gravitational time dilation from altitude differences creates variations of roughly 1 nanosecond per foot of elevation. These effects are real and measurable with atomic clocks, but they're negligible for everyday timekeeping. But the story goes deeper than just small effects. The very act of synchronizing clocks across Earth requires us to grapple with fundamental questions about the nature of time itself. What does it mean for distant events to be simultaneous? How do we establish a global time standard when simultaneity is relative? The answers reveal that our synchronized Earth time is actually a carefully constructed convention rather than a fundamental aspect of reality. The global positioning system provides the most striking example of how we must account for relativistic effects in everyday technology. GPS satellites experience both time dilation from their orbital motion, which makes their clocks run slow, and gravitational time dilation from being farther from Earth's center, which makes their clocks run fast. These effects nearly cancel each other out, but the small remaining difference of about 38 microseconds per day must be corrected for GPS to work properly. Without these relativistic corrections, GPS would accumulate errors of about 6 miles per day. making the system useless for navigation. The fact that your smartphone knows your location to within a few feet depends on engineers, carefully accounting for the relativistic nature of time. Einstein's seemingly abstract theories of space and time turn out to be essential for the most practical modern technologies. The deeper mystery is how Earth managed to become a special frame of reference where clocks can appear to stay synchronized. This isn't because Earth occupies some privileged position in the universe, but because all clocks on Earth share similar motions and gravitational environments. We've unconsciously created a local time coordinate system that papers over the relativistic nature of time within our planetary neighborhood. But this harmony is fragile and breaks down when we venture beyond Earth. Astronauts on the International Space Station experience time running slightly faster than on Earth's surface due to reduced gravity, gaining about 0.01 seconds per year. Future missions to Mars will require completely new approaches to timekeeping as the relativistic effects become much more pronounced across interplanetary distances. If you're fascinated by how the most fundamental aspects of reality connect to everyday experience, subscribe and hit thumbs up. And here is something to ponder. If you synchronized two identical clocks and then carried one around the world while leaving the other stationary, how much would they differ when you returned? Comment your prediction below. I'll pin the most insightful calculation. Tonight we're going to unravel one of the most beautiful paradoxes in physics. How clock synchronization on Earth reveals both the profound relativity of time and the ingenious ways that nature and human technology work together to create the illusion of absolute simultaneity. We'll discover how the everyday act of checking the time connects to some of the deepest insights about space, time, and the structure of reality itself. The story of synchronized Earth time illuminates the subtle dance between fundamental physics and practical technology, showing how Einstein's revolutionary insights about the nature of time have been seamlessly integrated into the fabric of modern life. Every GPS navigation, internet timestamp, and coordinated global event depends on our sophisticated understanding of temporal relativity. This isn't just about clocks and technology. It's about understanding how human beings have learned to live and work within the relativistic universe that Einstein revealed, creating islands of temporal coordination in an ocean of relative time. The apparent agreement of Earth's clocks masks a much deeper story about the nature of time itself and humanity's remarkable ability to adapt to the strange reality of a relativistic cosmos. Now let's begin our exploration of time's deepest mysteries, where the ticking of clocks reveals the fundamental structure of space, time, and causality itself. Chapter 1. The Nature of Time. Understanding why clocks on Earth appear to stay synchronized despite the relativity of time requires first grappling with the level understanding why clocks on Earth appear to stay synchronized despite the relativity of time requires first grappling with the fundamental question of what time actually is, a deceptively simple question that has puzzled philosophers and physicists for millennia. Time governs every aspect of our existence, yet when we try to define it precisely, we encounter mysteries that challenge our most basic assumptions about the nature of reality. Ancient civilizations conceptualized time as cyclical, following the patterns of celestial motions, seasonal changes, and human life cycles. The Babylonians divided days into hours, minutes, and seconds based on astronomical observations, creating the temporal framework we still use today. However, these early concepts treated time as an absolute background against which events unfold, a universal clock that ticks the same for everyone, everywhere. Isaac Newton formalized this intuitive notion in his Principia Mathematica, describing absolute time that flows equably without relation to anything external. In Newton's universe, simultaneity was absolute. If two events happened at the same time, according to one observer, they happened simultaneously for all observers. This absolute time provided the foundation for classical mechanics and seemed to match everyday experience perfectly. The Newtonian view dominated physics for over 2 centuries because it aligned with human intuition and successfully described most observable phenomena. Clocks could, in principle, be synchronized across any distance instantaneously. Time zones represented mere human conveniences for organizing social activities, rather than reflecting fundamental physical constraints on synchronization. However, the late 19th century brought experimental challenges to this absolute time framework. The Michelson-Morley experiment, designed to detect Earth's motion through the hypothetical luminiferous ether, produced null results that suggested something fundamental was wrong with our understanding of space and time. Light appeared to travel at the same speed regardless of Earth's motion, contradicting expectations based on absolute time and space. Dr. Albert Einstein resolved these contradictions through his special theory of relativity in 1905, revealing that space and time are intricately connected in a 4-dimensional space-time manifold. Time is not absolute but relative. It depends on the motion of the observer and cannot be separated from spatial coordinates. The speed of light in vacuum represents not just a physical constant, but the fundamental speed at which causal influences propagate through spacetime. Special relativity demolished the concept of absolute simultaneity. Events that appear simultaneous to one observer occur at different times for observers moving relative to the first. This relativity of simultaneity emerges from the finite speed of light and the requirement that physical laws remain the same in all inertial reference frames moving at constant velocities. The mathematics of special relativity shows that time intervals between events depend on the relative motion between observer and the events being observed. Time dilation causes moving clocks to run slow relative to stationary ones, while length contraction causes moving objects to appear shortened in the direction of motion. These effects become pronounced only at speeds comparable to light speed, but are always present. Einstein's general theory of relativity, completed in 1915, extended these insights to include gravity and acceleration. General relativity reveals that gravity is not a force, but the curvature of spacetime caused by mass and energy. This curvature affects the flow of time itself. Time runs slower in stronger gravitational fields, an effect called gravitational time dilation. The equivalence principle, central to general relativity, states that gravitational and acceleration effects are locally indistinguishable. An observer in free fall experiences no gravitational effects locally, while an observer standing on Earth's surface experiences constant acceleration relative to free-falling reference frames. This principle connects gravitational time dilation to the time dilation experienced by accelerating observers. Modern physics has revealed time to be even stranger than Einstein imagined. Quantum mechanics introduces fundamental uncertainty into temporal measurements through the time-energy uncertainty principle. Quantum entanglement creates correlations between distant events that seem to transcend classical notions of temporal sequence and causality. Thermodynamics provides another perspective on time through the second law, which states that entropy tends to increase over time in isolated systems. This arrow of time distinguishes past from future in ways that fundamental physical laws, which are generally time reversible, do not. The thermodynamic arrow of time emerges from statistical mechanics and the special initial conditions of our universe. The psychological experience of time differs dramatically from physical time. Human perception of temporal duration varies with attention, emotion, and neurological state. The brain constructs our sense of now from sensory inputs that arrive at different times and are processed through neural networks with varying delays, creating a subjective present moment that has no direct correspondence to any objective physical instant. Cosmological perspectives reveal time's connection to the evolution of the universe itself. The Big Bang Theory describes how time began with the universe approximately 13.8 billion years ago. Before this cosmic origin, The concept of before becomes meaningless within current physical theories, suggesting that time might be as fundamental to existence as matter and energy. The measurement of time has evolved from astronomical observations to atomic transitions that provide increasingly precise standards. The international second is now defined by the hyperfine transition frequency of cesium-133 atoms, providing a reproducible time standard based on quantum mechanical processes rather than astronomical motions. This atomic time forms the basis for all modern precision timekeeping. Different theoretical frameworks propose varying relationships between time and other physical quantities. Some theories treat time as emergent from more fundamental quantum mechanical processes, while others consider time as fundamental as space and energy. The nature of time remains one of the deepest unsolved problems in theoretical physics. The block universe interpretation of relativity suggests that past, present, and future all exist equally. That time is more like a spatial dimension where all events exist simultaneously in four-dimensional spacetime. This eternalist view conflicts with our experience of temporal flow, but emerges naturally from the mathematical structure of relativity theory. Causal structure in relativity theory distinguishes between events that can influence each other through light, signals, time-like and light-like separations, and events that cannot, space-like separations. This causal structure provides an absolute framework within relativistic spacetime, even though simultaneity remains relative. Events with space-like separations have no definite temporal order. Their sequence depends on the observer as reference frame. The practical implications of time's relative nature become apparent in high-precision applications like GPS navigation, particle accelerator experiments, and astronomical observations. These technologies must account for relativistic effects to function properly, demonstrating that time relativity is not just theoretical, but essential for modern technology. Perhaps most profoundly, the nature of time connects to fundamental questions about consciousness, free will, and the meaning of existence. If time is relative rather than absolute, what does this mean for concepts like causality, identity, and moral responsibility? Understanding time's nature requires grappling with both mathematical physics and philosophical implications. The apparent synchronization of Earth's clocks occurs within this relativistic framework where time is fundamentally relative. The fact that clocks appear to agree reflects not absolute simultaneity, but rather the shared motion and gravitational environment of our planetary reference frame. This synchronization represents a local coordination rather than a universal truth about time. As we'll explore next, Einstein's special relativity reveals exactly how and why simultaneity becomes relative, showing that the very concept of at the same time depends critically on the observer as motion and the method used to synchronize distant clocks. Chapter 2. Einstein's Relativity. Albert Einstein's theories of relativity revolutionized our understanding of space and time, revealing that the apparent agreement of clocks on Earth masks a deeper reality where simultaneity is relative and time itself depends on motion and gravity. Understanding how these revolutionary insights emerged helps us grasp why clock synchronization presents such a profound challenge to our intuitive notions about the nature of time. The special theory of relativity emerged from Einstein's attempt to reconcile the laws of electromagnetism with the principle of relativity. The idea that the laws of physics should be the same in all inertial reference frames. Maxwell's equations describing electromagnetic phenomena predicted that light travels at a constant speed in vacuum, but this seemed to contradict the classical expectation that speed should add according to Galilean relativity. Einstein's brilliant insight was that the speed of light in vacuum is the same for all observers, regardless of their motion. This seemingly simple postulate, combined with the principle of relativity, led to revolutionary conclusions about the nature of space and time. If light speed is constant, then space and time must be relative. they must transform in ways that preserve light speed for all observers. The Lorentz transformation provides the mathematical framework for relating space and time measurements between different inertial reference frames. These transformations show that spatial and temporal coordinates are mixed when changing between reference frames moving at constant velocities relative to each other. Space and time are not separate, but form a unified four-dimensional spacetime. Time dilation represents one of the most striking consequences of special relativity. Dr. Hermann Minkowski formalized the spacetime concept by showing that special relativity can be understood geometrically. In Minkowski spacetime, events are represented as points in four-dimensional space with three spatial dimensions and one temporal dimension. The distance between events, called the spacetime interval, remains invariant under Lorentz transformations. The relativity of simultaneity emerges from the geometric structure of Minkowski spacetime. Events that are simultaneous according to one observer lie on a particular three-dimensional slice through four-dimensional spacetime. Different observers, moving relative to each other, slice spacetime differently, leading to different definitions of simultaneity. This relativity of simultaneity can be understood through Einstein's train thought experiment. Imagine lightning strikes hitting both ends of a moving train simultaneously according to an observer on the platform. An observer on the train, moving toward one strike and away from the other, will see the light from the forward strike arrive first and conclude that the strikes were not simultaneous. The key insight is that simultaneity depends not just on when events occur, but on how information about those events reaches the observer. Since light travels at finite speed, determining simultaneity requires a synchronization procedure. Different observers in relative motion will use different synchronization procedures, leading to different judgments about simultaneity. Length contraction provides another manifestation of spacetime mixing in special relativity. Objects appear contracted in their direction of motion by the same factor gamma that causes time dilation. This effect, combined with time dilation, preserves the speed of light as measured by different observers, while dramatically altering our concepts of space and time. The twin paradox illustrates how time dilation affects aging and the passage of time. If one twin travels to a distant star at high speed while the other remains on Earth, the traveling twin ages more slowly and returns younger than the Earth-bound twin. This effect is not merely apparent, but represents a real difference in the amount of time experienced by each twin. Causality remains preserved in special relativity through the light cone structure of spacetime. Events can only influence other events within their future light cone, the region of spacetime that can be reached by light signals. This causal structure provides an absolute framework, even though simultaneity is relative. The addition of velocities in special relativity differs from classical expectations due to the relativistic velocity addition formula. Velocities don't simply add arithmetically, but combine according to v equals v plus v 1 plus v j v c. This formula ensures that no material object can exceed light speed regardless of how velocities are combined. Mass-energy equivalence, expressed in Einstein's famous equation E equals mc, emerges from special relativity's treatment of energy and momentum. The rest mass of an object represents enormous stored energy, while kinetic energy contributes to relativistic mass. This equivalence has profound implications for nuclear physics and particle interactions. General relativity extends special relativity to include gravity and acceleration by describing spacetime as a curved four-dimensional manifold. The presence of mass and energy curves spacetime, and this curvature manifests as gravitational effects. Freely falling objects follow geodesics, straight lines in curved spacetime. The equivalence principle states that gravitational and acceleration effects are locally indistinguishable. An observer in a windowless elevator cannot determine whether they feel weight due to gravity or due to acceleration. This principle connects gravitational time dilation to the time dilation experienced by accelerating observers in special relativity. Gravitational time dilation causes clocks to run slower in stronger gravitational fields. This effect has been confirmed through numerous experiments, including the Pound-Rebka experiment measuring frequency shifts of gamma rays in Earth as gravitational field, and observations of time dilation near massive celestial objects like neutron stars and black holes. The curvature of spacetime affects not only the flow of time but also the geometry of space itself. Parallel lines can converge or diverge, and the angles of triangles may not sum to 180 degrees. These geometric effects become pronounced near massive objects and in the presence of strong gravitational fields. Gravitational waves represent ripples in spacetime itself, propagating at light speed and carrying energy away from accelerating masses. The detection of gravitational waves by LIGO and Virgo collaborations provides direct evidence for the dynamic nature of spacetime predicted by general relativity. Black holes represent the most extreme manifestation of spacetime curvature, where the gravitational field becomes so strong that not even light can escape. Near black holes, time dilation becomes extreme, and the familiar concepts of space and time break down at the event horizon and singularity. Cosmological solutions to Einstein's field equations describe the evolution of the universe as a whole. The expanding universe, dark energy, and the Big Bang all emerge from general relativistic cosmology, showing how spacetime geometry determines cosmic evolution on the largest scales. The mathematical formalism of general relativity uses tensor calculus and differential geometry to describe how spacetime curvature relates to mass and energy through Einstein's field equations. These equations represent one of the most beautiful and profound insights in theoretical physics, connecting geometry to physics in unprecedented ways. Modern tests of relativity continue to verify Einstein's predictions with increasing precision. Atomic clocks, GPS satellites, particle accelerators, and astronomical observations all confirm relativistic effects to extraordinary accuracy. These tests demonstrate that relativity is not just abstract theory, but fundamental to understanding nature. The philosophical implications of relativity challenge common-sense notions about the absolute nature of space and time. The block universe interpretation suggests that past, present, and future all exist equally, while the relativity of simultaneity undermines naive concepts about universal now moments. Perhaps most remarkably for our question about clock synchronization, relativity reveals that the apparent agreement of Earth's clocks represents a carefully constructed convention rather than a fundamental aspect of reality. The synchronization procedures we use assume specific definitions of simultaneity that work well within Earth's reference frame but break down for observers in relative motion. As we'll explore next, the relativity of simultaneity presents fundamental challenges to any attempt to synchronize distant clocks, forcing us to carefully examine what we mean when we say that clocks agree on the time. Chapter 3: Simultaneity and Synchronization. The concept of simultaneity events happening at the same time lies at the heart of why clocks appear to stay synchronized on Earth despite time's relativistic nature. Einstein's revelation that simultaneity is relative rather than absolute fundamentally changed how we understand temporal coordination and revealed that clock synchronization requires careful consideration of reference frames and synchronization procedures. Classical physics assumed absolute simultaneity. If two events occurred at the same time, according to one observer, they occurred simultaneously for all observers throughout the universe. This assumption made clock synchronization conceptually straightforward. Clocks could, in principle, be synchronized instantaneously across any distance, creating a universal now that applied everywhere. Einstein's special relativity shattered this assumption by showing that simultaneity depends on the observer's state of motion. Events that appear simultaneous to one observer occur at different times for observers moving relative to the first. This relativity of simultaneity emerges from the finite speed of light and the requirement that physical laws remain the same in all inertial reference frames. The Einstein synchronization procedure provides a method for synchronizing distant clocks that takes into account the finite speed of light. To synchronize two clocks separated by distance d, an observer sends a light signal from clock A to clock B at time t, according to clock A, receives a reflection at time t, and sets clock B to read t plus tt2 when the signal arrives. This procedure assumes that light takes the same time to travel from A to B as from B to A. However, this synchronization procedure is not unique. Different synchronization conventions can be chosen while remaining consistent with special relativity. The key insight is that simultaneity is not discovered, but defined through our choice of synchronization procedure. Different procedures lead to different definitions of simultaneity, all equally valid within their respective frameworks. Dr. Hans Reichenbach showed that any synchronization procedure can be parameterized by a parameter epsilon, where epsilon equals 1/2 corresponds to Einstein's synchronization. Other values of epsilon lead to different but equally valid synchronization conventions. The choice of epsilon reflects our arbitrary decision about how to coordinate time across space, rather than discovering some absolute truth about simultaneity. The relativity of simultaneity has profound implications for the concept of now. In classical physics, now extended instantaneously across the entire universe. In relativity, now becomes observer-dependent. Each observer's now corresponds to a different three-dimensional slice through four-dimensional spacetime. These simultaneity slices intersect for different observers, meaning that events in one observer's past can be in another observer's future. This relativity of temporal ordering applies only to space-like separated events, events that cannot influence each other through light signals. Causal relationships remain absolute, preserving the logical structure of cause and effect. The practical implications of simultaneity relativity become apparent when attempting to synchronize clocks across large distances. Consider trying to synchronize clocks in New York and Los Angeles. The 2,500-mile separation means that light signals take about 13 milliseconds to travel between the cities. Any synchronization procedure must account for this light travel time. If an observer in New York attempts to synchronize the Los Angeles clock by sending a radio signal which travels at light speed, they must decide how to account for the signal propagation time. The natural choice is Einstein's synchronization, but this choice represents a convention rather than a physical necessity. An observer moving relative to both cities would use a different synchronization procedure and reach different conclusions about simultaneity. The global positioning system illustrates how synchronization challenges are addressed in practice. GPS satellites broadcast time signals that allow ground-based receivers to determine their location by measuring signal arrival times from multiple satellites. The entire system depends on precise clock synchronization between satellites and ground stations. GPS synchronization must account for both special and general relativistic effects. The satellite's orbital motion creates special relativistic time dilation that makes their clocks run slow relative to ground clocks. Their higher altitude in Earth's gravitational field creates gravitational time dilation that makes their clocks run fast. These effects partially cancel, but the remaining difference of about 38 microseconds per day must be corrected for GPS to function properly. The synchronization of GPS clocks relies on Einstein's synchronization within Earth's reference frame. Ground control stations monitor satellite clocks and broadcast corrections to maintain synchronization. This procedure works because all components of the GPS system share similar motions and gravitational environments within Earth's frame of reference. Network Time Protocol (NTP) provides another example of practical clock synchronization across global distances. NTP synchronizes computer clocks worldwide through a hierarchy of time servers connected via the Internet. The protocol accounts for network delays and implements algorithms that estimate and correct for signal propagation times. NTP accuracy is limited by the variability and asymmetry of inter-routing paths. Unlike GPS, which uses controlled radio signals, Internet packets may take different routes in each direction and experience varying delays due to network congestion. Despite these challenges, NTP can achieve synchronization accuracy of milliseconds across global networks. International Atomic Time, TI, represents the most precise realization of coordinated time on Earth. TI is maintained through a weighted average of over 400 atomic clocks located at metrology institutes worldwide. The synchronization of these clocks requires careful accounting for relativistic effects and signal propagation delays between different laboratories. The definition of TI uses Einstein synchronization within Earth's reference frame, treating Earth as approximately an inertial reference frame for timekeeping purposes. This approximation works well because relativistic effects from Earth rotation and orbital motion are small compared to the precision of modern atomic clocks, but they become significant for the highest precision applications. Coordinated Universal Time, UTC, provides the basis for civil time worldwide and is derived from TAI with the addition of leap seconds to maintain synchronization with Earth's rotation. UTC represents a compromise between the precision of atomic time and the astronomical time based on Earth's rotation, which varies due to tidal forces and other effects. The synchronization of UTC across the globe relies on a network of atomic clocks and time transfer techniques, including GPS, two-way satellite time transfer, and fiber optic links. These methods achieve synchronization accuracies of nanoseconds to microseconds, enabling global coordination of financial transactions, communication networks, and scientific experiments. Frequency standards provide the foundation for all precision timekeeping and clock synchronization. Atomic clocks based on cesium, rubidium, hydrogen masers, and optical frequency standards achieve stabilities and accuracies that reveal relativistic effects in Earth-based experiments. The international second is defined by the hyperfine transition frequency of cesium-133 atoms. Optical atomic clocks using trapped ions or neutral atoms achieve even higher precision than microwave atomic clocks. These optical standards can detect gravitational time dilation due to height differences of just a few centimeters, revealing the relativistic nature of time in laboratory experiments. The synchronization of optical clocks across continental distances requires sophisticated techniques including frequency combs, fiber optic frequency distribution, and satellite-based comparisons. These methods enable clock comparisons at the level of 10 fractional frequency stability, opening new possibilities for tests of fundamental physics. Perhaps most remarkably, the apparent synchronization of clocks on Earth emerges from our choice to use Einstein synchronization within Earth's reference frame. This choice is not forced by physics, but represents a convenient convention that works well for most practical purposes. The agreement of Earth's clocks reflects our successful implementation of a particular synchronization convention rather than any absolute property of time itself. The study of simultaneity and synchronization reveals that time coordination is as much a matter of convention and choice as it is of physics. While the relativistic effects that complicate synchronization are real and measurable, the procedures we use to maintain temporal coordination reflect human decisions about how to organize time within our local reference frame. As we'll explore next, the phenomenon of time dilation, the actual slowing of time for moving clocks, provides the physical foundation for understanding why synchronization procedures work differently for different observers and why Earth's shared motion allows for effective temporal coordination. Chapter 4. Time dilation effects. Time dilation represents the heart of why relativistic effects do and obviously disrupt clock synchronization on Earth. These effects are real and measurable, but incredibly small at the speeds and gravitational field strengths we experience in everyday life. Understanding the magnitude and nature of time dilation effects reveals how Earth manages to maintain the appearance of synchronized time despite the fundamentally relativistic nature of temporal flow. Special relativistic time dilation occurs when objects move at high speeds relative to each other. For typical Earth-based motions, time dilation effects are extraordinarily small. A car traveling at 60 miles per hour, 27 meters per second, experiences time dilation of only about 410, meaning the car's clocks run slow by approximately 0.1 femtoseconds per second. Commercial aircraft flying at 500 miles per hour experience time dilation of roughly 310, still completely negligible for practical timekeeping. Earth's rotation creates slightly larger time dilation effects. At the equator, Earth's surface moves at approximately 1,040 miles per hour, 465 meters per second, due to rotation. This creates a time dilation factor of about 1.2 times 10, causing equatorial clocks to run slow relative to polar clocks by roughly 100 nanoseconds per day. While measurable with atomic clocks, this effect remains tiny for ordinary timekeeping. Earth's orbital motion around the Sun produces more significant time dilation. Earth travels at about 67,000 miles per hour, 30 kilometers per second in its orbit, creating a time dilation factor of approximately 510 des. This causes all Earth-based clocks to run slow relative to the Sun's reference frame by about 0.4 milliseconds per day. However, since all clocks on Earth share this orbital motion, they remain synchronized relative to each other. Dr. Haffel and Keating performed the first direct test of time dilation using commercial airliners in 1971. They flew atomic clocks around the world and compared them with reference clocks that remained stationary. The flying clocks showed exactly the time differences predicted by special and general relativity, confirming time dilation effects at modest velocities. The Haffel-Keating experiment revealed both special and general relativistic effects. The eastward flying plane moved faster relative to Earth's center due to adding to Earth's rotation, while the westward flying plane moved slower. Additionally, both planes flew at higher altitudes where gravitational time dilation caused their clocks to run faster. The experiment carefully accounted for both effects. Gravitational time dilation creates additional temporal effects that depend on position in Earth's gravitational field. Clocks run slower in stronger gravitational fields, meaning sea-level clocks run slightly slower than mountaintop clocks. The effect is approximately 1.1 times 10 per meter of altitude, or about 1 nanosecond per 9 meters of height difference. This gravitational time dilation has been measured with extraordinary precision using atomic clocks. Experiments have detected gravitational time dilation effects due to height differences as small as 33 centimeters, demonstrating that time literally flows at different rates at different elevations on Earth's surface. The Pound-Rebka experiment in 1959 provided the first precision test of gravitational time dilation by measuring the frequency shift of gamma rays climbing out of Earth's gravitational field. Photons lose energy as they climb against gravity, causing their frequency to decrease in exactly the amount predicted by general relativity. Modern optical atomic clocks can detect gravitational time dilation effects that would be completely imperceptible to any biological or mechanical timekeeper. These clocks reveal that time flows differently, even between laboratory floors in the same building, showing that gravitational time dilation is a real phenomenon affecting every moment of our existence. The combination of motional and gravitational time dilation creates complex patterns of temporal flow across Earth's surface. Equatorial regions experience both faster motion due to rotation and slightly weaker gravity due to centrifugal effects and Earth's oblate shape. These competing effects partially cancel each other out, but don't completely eliminate variations in time flow. GPS satellites provide the most practically important example of time dilation effects in everyday technology. These satellites orbit at approximately 20,200 kilometers altitude at speeds of about 14,000 kilometers per hour. Their high speed creates special relativistic time dilation that makes their clocks run about 7 microseconds per day slow relative to Earth's surface. However, GPS satellites also experience weaker gravity than Earth's surface, creating gravitational time dilation that makes their clocks run about 45 microseconds per day fast. The net effect is that GPS satellite clocks run approximately 38 microseconds per day fast relative to ground-based clocks if no corrections are applied. Without accounting for these relativistic effects, GPS would accumulate position errors of about 10 kilometers per day, making the system completely useless for navigation. The GPS system applies real-time corrections for time dilation effects, demonstrating that relativity is essential for modern technology rather than just an abstract theoretical concern. Dr. Neil Ashby has extensively studied relativistic effects in satellite navigation systems, showing how various orbital parameters and Earth's gravitational field create complex patterns of time dilation that must be carefully modeled for precision applications. These effects include not only time dilation, but also relativistic frequency shifts and signal propagation delays. The International Space Station experiences time dilation effects that are measurable, but small enough that they do insignificantly affect mission operations. Astronauts on the ISS age slightly slower than people on Earth's surface due to their high orbital speed, but they also age slightly faster due to reduced gravity. The net effect is that ISS astronauts age about 0.01 seconds less per year than Earth-bound humans. Particle accelerator experiments routinely observe dramatic time dilation effects with subatomic particles traveling at significant fractions of light speed. Muons created in cosmic ray collisions in Earth's upper atmosphere should decay long before reaching the surface. But time dilation allows many to survive the journey. This provides continuous confirmation of special relativistic time dilation. The GPS system also reveals how time dilation effects scale with orbital parameters. The higher a satellite's orbit, the faster its clocks run due to reduced gravity, while faster orbital speeds cause clocks to run slower. These competing effects create optimal orbital altitudes where time dilation effects are minimized. Future space missions will encounter much more significant time dilation effects as spacecraft travel to other planets and potentially to nearby stars. A round trip to Mars involves both high-speed travel and extended periods in different gravitational environments, creating time dilation effects that could accumulate to seconds or minutes over mission durations. Interstellar travel would involve extreme time dilation effects that would fundamentally alter human experience of time. A spacecraft traveling at 90% light speed would experience time dilation factor of about 2.3, meaning that a 10-year journey would age the crew only 4.4 years, while decades pass on Earth. These effects become the dominant consideration for any seriously fast interstellar travel. Perhaps most remarkably, the study of time dilation reveals that the apparent synchronization of Earth's clocks emerges, because all terrestrial timekeepers share very similar motions and gravitational environments. The time dilation effects that do exist on Earth are either too small to matter for everyday purposes or affect all clocks in nearly the same way. The precision of modern atomic clocks has reached the point where gravitational time dilation effects are easily measurable even within laboratory buildings. This has opened new possibilities for using clocks as sensors of gravitational fields and for testing fundamental physics. But it also reveals the subtle ways that time flows differently, even within our local environment. Understanding time dilation effects shows that the temporal harmony we observe on Earth represents a remarkable coincidence of scale. The relativistic effects are large enough to be scientifically interesting, but small enough that they don't disrupt our everyday experience of synchronized time. This balance has allowed human civilization to develop without confronting the full strangeness of relativistic time until we achieve sufficient technological precision. As we'll explore next, the gravitational effects that contribute to time dilation also influence clock synchronization in subtle ways, requiring us to carefully consider how Earth's mass and rotation affect the flow of time across our planet's surface. Chapter 5. Gravitational Effects. Earth's gravitational field creates subtle but measurable variations in the flow of time across our planet's surface, affecting clock synchronization in ways that become apparent only with the most precise atomic timekeepers. Understanding these gravitational effects on time reveals another layer of complexity in maintaining synchronized clocks and shows how general relativity influences every aspect of temporal coordination on Earth. The fundamental principle underlying gravitational time dilation emerges from Einstein's equivalence principle, which states that gravitational and acceleration effects are locally indistinguishable. An observer in a gravitational field experiences the same effects as an observer undergoing constant acceleration in free space. This equivalence connects gravitational time dilation to the time dilation experienced by accelerating objects in special relativity. In general relativity, massive objects curve spacetime, and this curvature manifests as gravitational effects. The curvature also affects the flow of time itself. Time runs more slowly in regions of stronger gravitational fields. This effect is not merely apparent, but represents actual differences in the rate of physical processes, including the ticking of atomic clocks. Earth's gravitational field strength varies significantly across its surface due to several factors. The inverse square law means that gravity is stronger at sea level than at higher altitudes. Additionally, Earth's rotation creates centrifugal effects that slightly reduce the apparent gravity, particularly at the equator. Earth's oblate shape, caused by rotation, also creates variations in gravitational field strength. The gravitational time dilation effect can be calculated using the metric tensor that describes spacetime curvature in Earth's vicinity. Near Earth's surface, the time dilation factor is approximately 1 plus GHc, where g is local gravitational acceleration, h is height above a reference level, and c is the speed of light. This gives a time dilation rate of about 1.1 times 10 per meter of elevation. Dr. Robert Pound and Glenn Rebka first measured gravitational time dilation in Earth's field using the Mux-Bauer effect in 1959. Modern measurements of gravitational time dilation achieve extraordinary precision using optical atomic clocks. These instruments can detect height differences as small as a few centimeters by measuring the resulting gravitational frequency shifts. The NIST optical clock experiments have demonstrated sensitivity to gravitational potential differences corresponding to height changes of about 2 centimeters. The variation of gravitational time dilation across Earth's surface creates challenges for maintaining synchronized time. A clock at sea level runs slower than an identical clock on a mountain top by about 1 nanosecond per 9 meters of elevation difference. For the highest mountains on Earth, this corresponds to time differences of nearly 100 nanoseconds per day. These altitude-dependent time differences must be accounted for in high-precision applications. The International Atomic Time (TI) coordinate system includes gravitational corrections that reference all contributing clocks to a standard gravitational potential. This ensures that time differences due to altitude don't affect the global time standard. The Global Positioning System provides the most visible example of gravitational time dilation effects in everyday technology. GPS satellites orbit at approximately 20,200 kilometers altitude, where Earth's gravitational field is significantly weaker than at the surface. This causes satellite clocks to run about 45 microseconds per day faster than surface clocks due to reduced gravity. The gravitational correction for GPS is much larger than the special relativistic correction from orbital motion. Without gravitational time dilation corrections, GPS would accumulate position errors exceeding 10 kilometers per day. The GPS system continuously applies these corrections, making Einstein's theory of gravity essential for modern navigation technology. Earth's rotation creates additional complications for gravitational time effects through frame dragging, also known as the lens-thirring effect. Rotating massive objects drag space-time along with their rotation, creating additional gravitational effects beyond those caused by mass alone. These effects are tiny for Earth but measurable with extremely sensitive experiments. The Gravity Probe B mission, launched by NASA in 2004, successfully measured frame dragging effects around Earth using gyroscopes in polar orbit. The experiment detected the tiny precession of gyroscope orientation caused by Earth's rotation dragging spacetime, confirming general relativity's predictions about how rotation affects spacetime geometry. Tidal forces create additional gravitational complications that affect precise timekeeping. Earth's gravitational field is not perfectly uniform, but varies due to the gravitational influence of the Sun, Moon, and other celestial bodies. These tidal effects create time-varying gravitational fields that can influence the most sensitive atomic clocks. The lunar tides, which cause measurable deformation of Earth's solid surface, also create periodic variations in gravitational time dilation. These effects are extremely small, but potentially detectable by networks of optical atomic clocks. Such measurements could provide new tests of general relativity and insights into Earth's internal structure. Geophysical effects contribute to local variations in Earth's gravitational field that can influence precision timekeeping. Underground mass distributions, mountain ranges, and even large buildings create gravitational anomalies that affect the local flow of time. While these effects are far too small to notice in everyday life, they become significant for the most precise atomic clocks. The emerging field of chronometric geodesy uses atomic clocks to measure gravitational field variations and map Earth's gravitational potential with unprecedented precision. By comparing clocks at different locations, scientists can determine elevation differences to centimeter accuracy and potentially detect subsurface mass distributions. Underground laboratories used for physics experiments often require special consideration of gravitational time effects. Particle accelerators and other precision instruments may need to account for the local gravitational environment when synchronizing timing systems. The depth underground can create measurable gravitational time dilation effects. Ocean dynamics create temporal variations in gravitational fields due to water mass redistribution. Large-scale ocean currents, seasonal variations in water storage, and even major storm systems can create gravitational effects detectable by precision clocks. These effects connect timekeeping to Earth system science and climate monitoring. The Global Geodetic Observing System, GGOS, coordinates worldwide measurements of Earth's gravitational field using various techniques including satellite gravity missions, terrestrial gravimetry, and potentially atomic clock networks. Understanding gravitational field variations is crucial for precise navigation, geodesy, and Earth science applications. International time transfer must account for gravitational effects when comparing clocks at different locations. The most precise time transfer techniques, such as two-way satellite time and frequency transfer, TWSTFT, and GPS carrier phase measurements, include corrections for gravitational time dilation differences between stations. Future developments in optical atomic clocks may achieve sensitivity to gravitational effects that are currently undetectable. These instruments could potentially measure gravitational waves directly through their effects on time flow, opening new possibilities for gravitational wave astronomy using networks of ultra-precise clocks. The study of gravitational effects on time has applications beyond fundamental physics. Precision agriculture might eventually use gravitational time measurements to map subsurface water distribution or soil density variations. Similarly, geological surveys could use clock networks to detect underground mineral deposits or monitor volcanic activity. Perhaps most remarkably, gravitational effects on time reveal that even Earth, as familiar surface, harbors subtle temporal complexities that challenge simple notions of synchronized time. The gravitational variations across our planet mean that time literally flows at different rates in different locations, creating an intricate temporal landscape that we navigate without awareness. The fact that clocks appear synchronized on Earth despite these gravitational variations reflects both the small magnitude of the effects and our unconscious adoption of synchronization conventions that account for predictable gravitational differences. The apparent harmony of Earth time emerges from sophisticated technical corrections, rather than any fundamental uniformity in time's flow. As we'll explore next, Earth's rotation adds another layer of complexity to temporal coordination, creating reference frame effects that influence both timekeeping and the fundamental nature of simultaneity across our rotating planet.